Okay. Good afternoon. Welcome back to the weekly live discussions on the NPTEL course, Wheel Mobile Robots. So we have reached at week 7 of this course. So in total, there are lectures worth of 8 weeks. So we have now reached week 7 towards the nearing the end of the course. And after week 8, we may also have one more session, probably to cover all the topics in brief, to summarize whatever we have discussed throughout the duration of this course. So, yeah, we'll that being put aside, we will get on with the session. So, Umar is participating in this lecture series or in this tutorial session. I hope you have gone through the sessions. So briefly speaking, regarding week 7, we are basically covering the topic of motion controllers for wheel mobile robots. We start by discussing its history, what were the recent trends in during each of these decades. And on further, going further into the lectures, we also discussed what are the different kinds of motion controls that we could employ. We have covered open loop controllers. We have covered closed loop controllers. We have also classified motion controllers based on whether it is a purely kinematic controller or whether it is a dynamic controller. And we have also discussed multiple cases of either of these classifications. Like, for example, in kinematic control, we have discussed simple inverse differential kinematic control. We have also discussed computed velocity input controls. Then, in the case of dynamic control, we have discussed the open loop controller called inverse dynamics control, and a closed loop controller called computed torque control. So, like, we'll discuss all this in brief, whatever that is being covered on week 7 in brief, and we'll also discuss some sample questions. So that will be the agenda for this live session. Okay, so moving on. So, as I've already said, this week is all about motion controllers. So I thought it would be better if you discuss about what a motion controller is. So we'll have some key definitions. So motion controller emphasizes these 3 points. The first being it is a subfield of automation encompassing the systems or subsystems involved in moving parts of machines in a controlled manner. Right? So, like, as you can see, if you are taking a robotic system in particular, it basically consists of multiple systems or a series of rigid bodies connected or constrained by different kinds of joints. And yeah, we would want to control the linkages of rigid bodies in a controlled manner, actually. Like, for example, if you consider a robotic arm or, for example, a mobile robot, our objective is to exactly drive the mobile robot along a desired trajectory. Or if you want to make a robot go to a specific point, we can actually regulate the mobile robot to navigate to that specific point. And this entire processes of making systems move or behave in a controlled manner is what defines a motion controller. Then what does this steps to say? It says motion controller is often closed loop. For example, it basically computes the next control input to be given onto this actuators, and it will also take feedback from the sensors, like what the robot is currently doing, to get information from the environment about its position, about its velocity, accelerations, probably its heading, angular position, velocity, accelerations. So it will incorporate closed loop also, and it monitors the actual path and correct for position and velocity errors. For example, like if the robot start position is over here and the robot goal position is over here, we want the robot to track this particular trajectory, right? And for example, this is our desired start position and desired goal position. And our mobile robot is actually starting somewhere else, maybe here. So motion control ensures that the mobile robot basically tracks this entire trajectory. For example, if it starts from here, it will converge to the start position, then it will try to track along this desired position. right? And if there are some errors, like if the motion controller feels that the robot is actually deviating away from the desired trajectory, it will compensate, or it will try to bring back the trajectory to the desired trajectory. Depends on how you design the controller. And point three states a motion controller contains the motion profiles and target positions for application and creates the trajectories for motors and or actuators. So motion profile basically is something what defines a trajectory. So it comprises of the start position, the goal position, the initial velocities and acceleration, the final velocities and acceleration, and for each of these time steps, you can divide this. If you begin from a start time and an end time, you can basically discretize this entire trajectory into finite, uh, very infinitesimal time steps, and how a robot should uh, move would be defined by the instantaneous angular position, velocities, and accelerations at each of these time steps. So that is what a motion control does. It basically pulls this motion profiles from a trajectory planner, and based on the trajectory planner, the motion controller gives this appropriate actuation commands into this actuator so that the robotic system can realize that specified trajectory. Okay, that is about motion controller and more or less its functions. And why do we need motion controllers actually? Because like as you have like if you can recall what we have covered in dynamics, this entire behavior of this robot, we can always define it using the robot's equations of motion, right? For example, if you consider everything in task space, the equations of motion would look something like tau would be d of theta dot plus n of theta. Right? This is how the equations of motion look like, and this is how we expect the mobile robot to behave. Right? If that is the case, then why do we need motion controller? And these are the reasons. The reason one being, for the robots, it's impossible or very difficult to obtain an exact dynamic model of the robot. For example, like no matter however hard you try or however accurately do you try to model the dynamic model, there will be some change of parameters because you cannot exactly estimate this inertia matrix or whatever be inside this Coriolis and centrifugal effects vector. Because, for example, like you may model a robot without any joint clearances, maybe you may not even consider the fastness, washers, weight of the washers, and all those things. But when you actually assemble a robot, there will be some joint clearances, obviously, because there are some manufacturing tolerances happening. And there could be some of the parts that you may not have included in the model. For example, weight of the washers and all those things. It could be it could even though its effect is less, it could have an impact on the values of this mass matrix, and there could be things that you might not even have considered in the model. For example, this model what we have depicted here, it does not account for friction in each of these joints. So friction is basically unmodeled, but as you know, like if you assemble a system in real life, there will be some sort of influence due to friction because there will be some sort of a dissipative forces within the system. And here you don't have any dissipative forces in the system. So that is actually one reason. Like you cannot exactly you cannot have an exact dynamic model. So because of that, if you try to control a robotic model with this alone, it may not track the trajectory that you wish. It may deviate slightly from the desired trajectory. Then the second reason be the presence of external disturbances and parameter variations, which are inevitable in robots. So the external disturbances could mean, the effects that is not again being modeled. For example, unprecedented external forces. Like as the robot is moving, it may probably collide some obstacle or it may navigate along a rough terrain. So there could be some forces that we may not be able to predict while modeling or while deciding this trajectory. So that could be this external parameters. For example, if the robot is moving outdoors, the wind effect could have a significant effect on how it follows its trajectory. So that could also be one of the factors. And the other thing is parameter variations. So like, for example, whatever we have initially modeled the robot, whatever parameters we have considered during the initial modeling of the robot, it may change over time because of wear and tear and all those other aspects. So that is also one of the reasons why we need a motion controller. So because with the dynamic model alone, we won't be able to control a robot along its exact trajectory. So that is why we need some sort of a feedback so that if the robot feels like it is actually deviating away from the desired trajectory, the controller should take appropriate action so that it can be brought back to the uh, desired trajectory or desired course of actions. Yeah, so that is about why do we need motion controllers, the relevance of motion controllers in robotic systems. And later in the lectures, we have also covered the current or maybe the how the trends in motion controller evolved from around 1970s all the way to the present learning. So earlier in classical robotics, during the time of 1970s, uh, the motion controller were mostly based on models, actually, mostly based on the dynamic models. So we control the robot based on the dynamic model of the robot. For example, this one, how we are represented in DAS space, would be d of zeta, zeta dot plus n of zeta. So this is what we actually used for controlling a robot, just the models. It did not have any sensory capabilities. Or with this we never had to have any, or we didn't actually have reliable sensing uh, tools. So even though this could have using the dynamic model alone or using the models alone could have some potential drawbacks that we can see in the upcoming slides. But this is what earlier classical robots was based on, purely on model. Then during 1980s, it actually pivoted to an entire different scheme. Now it does not even rely on models. So controlling a robot, we never actually considered the models at all. It only relied on sensing. Like for example, if the robot is actually expected to trace or track the desired trajectory, we would use the sensors available to the robot to see whether the robot is exactly matching the trajectory or it is deviating away from the trajectory. And if it is deviating, you can have the appropriate control input so that you can bring it back to the desired trajectory. So, like for example, you might know this PID control. Like the PID control would simply mean we would give a proportional control signal that is proportional to the error, and we would also uh, it's sum of the proportional value of the error, then the derivative of the error plus the integral of the error. So each of these term PID has different relevances actually. Like for example, if your robot is having some sort of a steady state error, maybe if the line I have drawn here at the top is the desired path or maybe a desired parameter and your actual is actually only reaching, there is actually a slight deviation between the actual and the desired at steady state, you can basically compensate or account for this steady state error using this integral term, because this integral term would basically accumulate all the errors and eventually make this error disappear as time goes to infinity. And derivative error is basically anticipatory. Like if the robot is feel like the error is actually going, the rate of change of error is actually increasing, it will give you an appropriate control action. So all these things never had to do anything with models. It was purely sensory. So that is what reactive paradigm is about. And then during later 90s, this was basically a mix of model and model control as well as reactive control, like model based on higher levels and reactive on lower levels. For example, higher level means at the manipulator level. For example, this is more relevant in robotic manipulators. For example, if you want essentially robotic manipulators comprises of CD linkages of multiple bodies. And you would want your end effector to track a specific trajectory. And in order for you to do that, you have to exactly coordinate or exactly know how these joints are actually moving. That is at the higher model level. And if you at the lower level basically implies at the actuator level. So if you want to control the actuators, you would have to the actuators controlling the actuators was purely based on sensory feedback, whereas in the case of the manipulator arm, you would use whatever information that you can get from the model, like how you model the robot manipulator using its own equations of motion. So that is another aspect, how you model this, because model base would be very efficient in real-time computation. This will be very relevant in case of robotic manipulators. Okay, so that was about hybrid models. And later we use, during mid 90s, we use probabilistic robotics. So you might have heard about this when we were discussing, error propagation and all those things during week 4. So this is all about seamless integration of models and sensing. So if you can recall how we did this error propagation, uh, we use whatever information we can actually get from odometry and whatever information we can get from sensors, and we basically fuse these two information so that we can estimate what the probability of where the robot would be at a later stage. So that is about probabilistic model. And as you know, like since we cannot exactly model an error, we can assume the error to follow a distribution. For example, the normal distribution. So that is in principle what this probabilistic robust is about. It's all about inaccurate models. It basically accepts the fact that the model of a robot that we have is inaccurate. And the sensing is also not perfect because whatever data we are getting from the sensors, those will be riddled with noises, and the sensors may also have some sort of errors, that is characterized by the sensors covariance of metrics. So yeah, that would be more or less take probabilistic robots basically takes the inaccuracies of the model into account, as well as the inaccuracies or limitations in the sensors. And during uh, 2015, recently, we have also used data-driven control actually. So we would want to train probably a neural network or machine learning model uh, with a data set, depending on how the robot would behave, and based on that, we can actually use that model or a data-driven model in order for us to control a robot using data-driven learning as well as reinforcement learning. So as the robot is operating, it keeps on getting new data and it further acquires new knowledge, and hence it will be able to uh, train on its own. Then, yeah, again, what are the procedures of motion control and what are the objectives of motion control? So basically, the procedures of designing a motion control can be summarized as follows. So the first and foremost important thing would be familiarization of the physical system under consideration. So like strictly from the point of view of a robotic system, we now know how to model the robotic system, and we would know how to physically model it using this dynamic equations of motion, right? We know how to model that actually, how it behave physically. And the second phase basically comes to modeling actually, how to model it, whether it is, if we are restricting ourselves within the kinematic model, that is fine. And if we also need to take the dynamic effects into this account, if the robotics highly dynamic, if it is very fast, then the inertial forces will have to be taken account. So in that case, the modeling choices and assumptions will have to be taken care of during this step. And the third stage would be the control specifications. Like as we are designing a controller, we would also need to specify the performance that we expect from a motion controller. For example, like if you want the controller to converge to the desired trajectory very rapidly, the rise time should be minimal. Or maybe if you want to eliminate the overshoots and probably the oscillations, how should the damping be, how fast the control should react, how aggressive the PID parameters should be. All these things can be tuned or should be tuned based on the control specifications, depending on how the user would want the robot to behave. And the objectives of the controller comprises of stability. So the first and foremost priority for designing a controller would be the stability of the controller. Like for example, if you consider this dynamic equations of motions for a mobile robot, that would be d of zeta, zeta dot plus n of zeta. As you can see, like there is no dissipative term inside. There is no dissipative forces or dissipative terms inside this dynamic model. We haven't considered any of these dissipative forces, maybe friction or damping or any of those sort of things. So as you can see, this system, the mobile robot's dynamic model, is inherently quite unstable. Right. So if you keep on giving a control input, for example, if you keep on giving a constant control force, you can see that the robot keeps on getting accelerated without any bonds because there are no dissipative terms. So if you apply a force, the force causes the body to accelerate, and since there are no dissipative terms, even if you apply the constant force, it will keep on accelerating. So those are inherently unstable, and because of that it could have a lot of safety issues or maybe potential issues to the robot itself and probably to all the things the robot is interacting with in its environment. So in that regard, while designing a controller, stability itself is the most important criterion. Then comes regulation. Actually, regulation basically means if you have a state, maybe an initial state, and if you have a final state, how well the robot reaches from this initial state to the final state, irrespective of its position or velocity or derivatives, how its capability to reach its final stage. And trajectory tracking is basically like it's not just about the initial and final states. It also matters how each of these uh, individual time steps are also realized. So even now the path and right at which this each of this path or each of these points in this path is realized is also important. Basically a tracking problem. And further optimization. So basically, if you want to optimize the performance, maybe if the robot is starting from somewhere else and how fast it will converge to the desired trajectory, or maybe it could even converge it very late or as it reaches the goal point. So all these things, the tuning of this controller comes under optimization. How well the robot tracks and how fast it is to react to errors and all those sort of things. So that comes under optimization. So, despite we have all the different objectives for designing a motion controller, the primary objective or the most important objective would still be stability of the system. Okay, now moving on, the different classification of motion controllers. We can classify based on whether it is a motion-based controller or a model-based controller. So the motion-based controller, also call it as a model-free controller. So what I mean by model is it's dynamic model, how you physically model robotic system. If I can recall this again. So in case of a motion-free or a model-based control, it purely relies on feedback. So we disregard what is being told by or what can be inferred from the model of the robot. We disregard the model totally and we purely rely on sensory feedback. The thing is that like these controllers are actually universally does not have to be a robotic system. These are very easy to use. But the problem is these are actually sluggish because it's reactive. It depends on the sampling rate of the sensors and how fast you can, send back the control signal back to the actuators. And this could also cause some poor tracking performance, because like if you don't know how the model of the robot is, like over time there is you could deteriorate the values you use to control maybe the gains that you use to control a system could change over time because of eventual wear and tear and all those things. So eventually, it could have poor tracking error, even though it began very well. It could eventually lead to some poor tracking errors. And since due to the fact that it purely relies on the kind of sensors and the kind of actuators that you are using, it could also be very sluggish because it does not know how the robot is, how it does not have any idea about how the robot is going to react. It can only react to how the robot is actually. It cannot predict more or less. It can only react based on how the robot would behave. And in case of model-based control, it will have an idea, an approximate idea of how the robot would behave based on the model that we do. And that is much more comparatively efficient and simple because once you have derived this model, it'll be very easy. It will be very efficient to control a robot in real time. But the drawback is that you need to have an accurate model. So if the system that you are dealing with it has very high dissipative forces, maybe dampers or friction and all those things, this model may not be good enough because here you haven't modeled friction at all. So if you're dealing with friction and your model does not really account for friction, then performance may not be optimal. So in that regard, accurate models should be available if you are using model-based control. Okay, then moving on, there is also another kind of classification, what we call as robust and adaptive controls. So, how these become relevant while deciding a controller? What are robust controllers? What are adaptive controllers? We will see now. So, yeah, in the case of robotic controllers, we basically have a set of implicit assumptions, like while deciding or designing a robotic controller. So the two implicit assumptions are the model is accurately known or the constant physical parameters are accurately known. So like for example, again, if I recall this being the model, maybe for example, for the time being, for a change, I'll only consider the kinematics. Eta dot is j of sine to theta. And if you accurately know this model, for example, if you can accurately estimate all these constituent elements of this Jacobian, then only this model will work, right? Or for example, if you want to consider the dynamics also, maybe tau is v of theta dot plus n of theta. And as you can recall, the constituent elements of the mass matrix or this inertia matrix consist of the parameters such as the center of mass of the robot chassis and the mass moment of inertia about the vertical z-axis. So unless and until you exactly estimate what this mass and this moment of inertia parameters are, you cannot claim that you have accurately modeled the robotic system. And because of various issues, there could be some deviations from the estimated value and the true value. And that is one of the reasons, actually, where we use robust and adaptive controllers, because the model is, we assume that the model is accurately known and the parameters are also accurately known, but that is not the case, right? That being this implicit assumption, and how do we deploy or employ this motion robust controller? So what a robust control does is that it aims at controlling with a small error a class of mobile manipulators model is not accurately known with same control. So like for example, if it has some sort of an idea about the model, and it also is aware that the parameters could be within some bounds. For example, the mass could be within plus or minus 5 kilograms. If it knows its lower and higher limits, then controllers designed as robust controllers can perform even if there is a small error in estimating these parameters. Yeah, because like for in case of a mass matrix, over time the mass matrix, due to wear and tear, the parameters, mass as well as the moment of inertia could vary. And the feature of robust controllers is that even if there are deviations in the parameters, it could still control the robot satisfactorily using the same model. That is where this robust controller comes. And in case of adaptive controller, it deals with the uncertainty in system parameters or unknown constant parameters, and it requires the precise knowledge of the structure of the system. So, like for example, there could be applications where you might not even uh, remotely estimate the mass metrics or maybe the inertial the moment of inertia and probably the location of the center of gravity and all those things, because sometimes the system could be highly dynamic, and as a result you treat these parameters like in the earlier case it was given to us, but in adaptive controller we consider these constant parameters to be unknown or rather highly dynamic. So in either of these cases, this adaptive control is able to estimate these unknown constant parameters uh, as the system basically navigates. So, but the catch is that the precise knowledge of the structure of the system should be known. How the system is behaving, whether it is a second order system, whether it's a first order system. All these things should be need should we should know that in advance. Okay, then going further on the lectures, we have also discussed various controller strategies. For week 7, we have considered kinematic control, where we limit ourselves with the kinematic models. So, like for example, in applications where the robot is moving very slowly, then we may not even consider the forces due to inertia, the inertial forces, probably due to dynamic effects. Sorry, if the robot is more or less quasi-static, you only need to restrict yourself within kinematic model. And you also have seen dynamic control, like when the robot is no longer quasi-static and you cannot simply neglect the inertial forces and so forth. You also have to take the actuators into account, the dynamics of the actuators into account. Then at the end of the week 7, we have also discussed something called a cascaded control. It's also called a double loop control, where basically the inner loop is controlled by an outer loop, where the outer loop is basically kinematics and the inner loop is basically dynamics. So in order for us to control in order for us to control the inner loop, the dynamic loop, we want the outer loop to behave in a controlled manner so that we can drive all the steady state errors at the dynamic level to zero. So in order for us to do that, we have to tweak the outer loop, which is the kinematic loop. So that is what this cascaded control is about. Uh, yeah, three different kinds of loops. And within each of these control, we have also seen open loop and closed loop. In kinematic control, we have seen open loop and closed loop. In dynamic control also, we have seen open and closed loop. Cascaded control is basically a closed loop motion control. So yeah, we will get on with kinematic control actually. So kinematic control and probably two examples of kinematic control just to cover this summary. So in kinematic control, what are the desired parameters? So the desired parameters are the trajectory of the robot defined by this vector eta desired and the desired velocities eta desired dot. So you know how the robot is modeled kinematically. You have this eta dot is j of psi multiplied by theta, where eta is x, y, and psi, x dot, y dot, and psi dot, because it's eta dot, and you have this Jacobian matrix, and psi is nothing but u, v, r. And you can use this vector eta to define the desired trajectory of a robot, because eta is basically defined with respect to the inertial frame of reference, and that is how humans external to a robot would also perceive the motion of a robot. For example, if you can consider this to be this inertial frame of reference, maybe xi, yi, zi, and if there is a mobile robot with its own body frame of reference, maybe xb, yb, and this being the frame b. So the trajectory of the centroid of the frame of reference, it's intuitive for a human being to define it with respect to the inertial frame of reference, because that is what we are also based on. Because the observer will be based on the inertial frame of reference, and it will be easier for us to observe the robot's motion along or defined with respect to the inertial frame of reference. So most often we would specify the desired trajectory in terms of task space coordinates or inertial frame of coordinates. And if you have, that is what you have specified. You will specify the trajectory using the desired positions and desired velocities. And what are the available data that you have? You have this actual positions, eta of t. Actual positions, you can actually obtain it from the sensors. And you can also assemble the Jacobian matrix, whether it is J of n or inverse of the Jacobian matrix, because you know what the Jacobian matrix is. It's nothing but cos psi minus sin psi, cos psi, 0, 0, 1. This is what the Jacobian matrix would look like. And this is also readily available to us. So your objective is to find the control input zeta, right? In order for us to realize this desired end effector velocities, what should be the control input that you should be giving to the mobile robot? And the control input will be given, since the control input would be given to the mobile robot, it should be referred with respect to the robot's frame of reference. And that is why we call zeta as zeta as control input, actually, because that is also defined with respect to the robot's local frame of reference. And by designing the controller, what are our objectives actually? Why are we designing this controller for? So the objectives or the requirements is that the system should be asymptotically stable. For example, as the time tends to infinity, the actual position should converge to the desired position. For example, if over here, if I draw this as desired position, maybe desired, and we start from somewhere else, maybe if this is the actual start, and it may initially start from somewhere else different to desired start position. And as time progresses, the robot's trajectory should merge with the desired trajectory. And as time tend to 0, eta should tend to eta desired. For example, I label this as eta desired and I label this as eta. And as time tends to infinity, the error or the gap between eta desired and eta should vanish. Or if we call this parameter eta desired minus eta as eta tilde, the error basically, the difference between desired and actual, you can also pose this problem as time tend to infinity, this eta tilde should tend to 0. The error between desired and actual position coordinates should vanish as time tends to infinity. So that is what we call this system to be asymptotically stable. As time tends to infinity, the system should achieve its desired state. Okay, so now we will go with open loop control. So like, for example, the kinematic model of the robot to be eta dot as j of psi multiplied by zeta. This is how the you can model the robot kinematically. And if you are given a desired trajectory, zeta desired, or because this will be given, this is how you would want your robot to move. And if this is given, and if you simply plug this onto here, you will be able to figure out what should be the correct control input, right? So if this is given, then the control input zeta should be j of psi inverse eta desired dot. So this is basically the control input, right? And if you can recall, are there any feedback terms in it? Because the control input is nothing but j of psi inverse eta desired dot. And if you take a look at this, there is no term that is coming from the feedback. This is nothing but the velocity of the desired velocity vector, and j of psi is nothing but the Jacobian matrix. And for the control input, there are no terms that is coming from the sensors, or there are no feedback terms. So in this regard, the controller is basically nothing but open loop control. It's an open loop control. And yeah, this will only work under certain conditions, right? This will only work, like what example, if eta desired dot d is 0, right? If you only need to make the robot go from a start position to a final position without worrying about the tracking, or maybe without worrying about its position at each of the time steps, then eta desired dot would be 0, right? And if eta desired dot is 0, then the control input would also be 0. So in that regard, when the desired velocity coordinates are 0, you cannot use this controller because it will fail. And another reason would be if the initial condition of the desired trajectory and the initial condition of the actual trajectory are matching, then only this control law would work. Like for example, if this is the robot's, for example, if the desired trajectory starts from a start point, maybe start desired, and if this is probably, end desired, and if the actual robot is starting from the start desired, it will basically behave, or it will basically reach to the end desired position. But what happens if the starting position of the robot, actual starting position, is somewhat offset? If I recall this as start offset, and if I call this as end offset, and if you still use this control law, zeta equal to j of psi inverse theta desired dot, it will only go like this. It won't converge to the desired trajectory, because there was an initial error between desired start position and desired the actual start position. And if you can recall, since there are no feedback terms in the control law, there is no way to compensate for this error. That error will still remain the same. So instead of this robot to move from the start position and eventually converge it to the desired trajectory, it will only move like. So in that regard, this control law, this open loop kinematic velocity control law, would only work if eta desired d is not 0 and the initial position of the desired trajectory is equal to the initial position of the start trajectory. And the control input would be nothing but this. This is what we have seen earlier, right? And the scheme will not work if the initial position of the desired and the initial position of the actual is not equal, or if the velocity of the desired position coordinates or velocity coordinates, or with respect to the inertial frame of reference, is also 0. Then how do we go on with the closed loop kinematic control? So we have seen the limitations of the open loop controller. What about the closed loop controller? So our objective for using a closed loop controller is we would want the system to behave as per the first order differential equation, eta tilde as e raised to minus lambda t. So eta tilde is nothing but eta desired minus eta, the difference between desired and actual position coordinates. And why would we want our robot to behave as per this differential equation? So the simple answer is, if you plot this error eta tilde along one axis, and if you plot time along this axis, so what will happen to this term as time tends to infinity? So initially it may begin from some value, and as time tends to infinity, this value goes to zero actually. Asymptotically, it will go to zero. So that is how we want the robotic system to behave. Like as the time goes to infinity, we want all the errors to converge to zero. We don't want any errors in the system. So that will also guarantee the stability of the system as well as eliminating all the errors within the system. But how do we design a controller based on this requirement? That is the objective, right? So if you differentiate this equation, you will end up with this equation, right? Eta tilde dot plus lambda eta tilde will be zero. How do we get that? If you differentiate this will be eta tilde dot t. This will be equal to minus lambda e raised to minus lambda t, right? And as you can see, e raised to lambda t is eta tilde of t. So if I replace that, eta tilde of t minus lambda eta tilde of t, right? This will be equal to minus. So if I bring everything to other side, eta tilde dot of t plus lambda eta tilde of t, this will be zero. So this is nothing but a first order system. And it is guaranteed that as time tends to infinity, eta tilde tends to zero. And if we also know this eta tilde is nothing but eta desired minus eta. So if I further differentiate it, eta tilde dot would be eta desired dot minus eta dot. So if I substitute this onto this equation, what will you get? Eta desired dot minus eta dot plus lambda eta tilde t, this will be zero. And if I take this to the other side, you will end up with eta dot would be eta desired plus lambda eta tilde t. And as you know, the control input will always be given with respect to the body's frame of reference, because the actuators are attached to the body of the robot, and the control input will be given with respect to the robot frame of reference. So you also know eta dot is j of psi multiplied by zeta. So if you find out zeta and substitute into this equation, you will get the controller as zeta is nothing but j of psi inverse eta desired dot plus lambda eta tilde t. So what kind of control law is this? Is this a feed forward law, or is it a feedback law? Or in other ways, what are the feed forward and feedback laws? So as you can see, this is a feed forward law. This will come directly from the trajectory planner onto the controller. This is nothing but a feedback term, eta desired dot. And this term, eta tilde, that is actually the feedback term. So this is feed forward, and this is feedback term. Because eta tilde is nothing but the difference between the desired position and actual position. The desired position is what basically the operator defined, and the actual position is what you get from the sensors. So in that regard, since it compares the difference between the desired and actual position, this term is basically the feedback term. So this scheme or this control law is also called the computed velocity control law. That is about it. Now we will move to dynamics. So earlier we only considered the static problem, where there could be situations where we could ignore or neglect the mass and inertia of the robot, and we only need to consider the kinematics of the robot. Now in cases where the Dynamics cannot be neglected. We need to design a dynamic controller. So again, similar to the kinematic problem, we have the desired trajectory defined using eta desired dot, and eta desired double dot. So the desired position, velocities, and accelerations are given. And what are the things that are available to us? The actual position is available to us from the sensors. The Jacobian matrix and its inverse are also available because it is essentially nothing but cos psi minus sin psi, cos psi. We also have this actual velocities from the tachometers or encoders, whatever rotation sensors, velocity sensors that we are using. We also have this inertia matrix and the vector of Coriolis force. Because now we know how to model the dynamics of mobile robot, which is nothing but tau is d of theta dot plus n of theta. So we also have this. And again, our objective is to find the control input vector torque. Again, how do we do that? So again, our objectives are similar to the kinematics case. Our objective is the system should be asymptotically stable. For example, as the time tends to infinity, the position errors eta tilde should be 0, and the velocity errors eta tilde dot should also be 0. So we have constraints on position and velocities, and where eta tilde is eta desired minus eta, and eta tilde dot is eta desired dot minus eta dot. And similar to what we have seen in the previous case, in dynamics also we have an open loop strategy and a closed loop strategy where if you know the desired trajectory, the control input torque can be simply computed using this inverse dynamic method. So this is also called inverse dynamics control. So if you know theta desired dot, then you can estimate the actuator velocities using this control law, where the control input torque is d of theta desired dot plus n of zeta desired, where the theta desired dot is so and so. And why is this being explicitly specified? So the reason being, as I've already said, you know how this eta desired dot and zeta desired are connected using this Jacobian matrix. And if you want the robot to track a particular trajectory, it's always convenient for a human to define the trajectory with respect to the the initial frame of reference, because that is how we perceive the robot. It's not very convenient to define with respect to the body frame of reference. So if this is the requirement, and in this inverse dynamics controller, you want to find this theta desired dot, how will you make it? So if you further differentiate it, it will be eta desired double dot. This would be j dot of psi zeta desired plus j of psi zeta desired dot. So if you rearrange, zeta desired dot would be nothing but eta desired double dot minus j dot of psi zeta desired. This whole pre-multiplied by what would that be? J of psi inverse. And you have this zeta desired term again here. So we can substitute, instead of the zeta desired term here, we can substitute this term, because we prefer everything to be with respect to eta desired. So if you do that again, it will be zeta desired dot. This would be j of psi inverse eta desired double dot minus j dot of psi zeta. Instead of zeta desired, you can write it as j inverse psi eta desired dot. So this is exactly what it has been written over here, and this is the computed, the inverse dynamics control. So again, comparing it with the inverse differential velocity control, are there any feedback terms over here? No, because there are no feedback terms here because we only have feed forward terms. There are no feedback terms that is coming from the sensors. All of them are feed forward terms. And again, there are limitations actually. Like if zeta desired dot is 0, then this control strategy may not work satisfactorily. Or if there is a difference between the initial condition of the desired trajectory and the initial condition of the actual trajectory, if there is indeed a difference between these two trajectories, the robot may deviate from the desired trajectory. It may not even track the uh, desired trajectory. So that is the potential drawback of this thing. So it will, unless you maintain everything very particular, or unless you force the robot to start from the desired trajectory's initial position, then making this inverse dynamics open loop controller itself is quite challenging. So this is where the closed loop dynamic control comes, or the feedback dynamic controller comes. So just like what we did in the case of the velocity controller, here we want the robot to behave as per this second order uh, differential equation, where the dependent term is eta tilde. Eta tilde is nothing but the difference between the desired and the actual coordinates. Right? So if you force the robot to behave as per the second order differential equation, what will happen? So as time tend to infinity, eta tilde will tend to 0 and eta tilde dot will also go to 0. For example, the desired and the actual velocities will have converged, and the desired and actual positions will also have converged as time tends to infinity, rendering the system as stable. And from robot dynamics, we also know this equation actually from kinematics, right? For example, you know this basic equation, eta dot is j of psi multiplied by zeta. If you differentiate it, you will get this equation. And you also know this equation, right? From tau would be d of zeta, zeta dot plus n of zeta, right? So from this equation, how will you find zeta dot? Zeta dot would be this tau minus n of psi, the whole pre-multiplied by d inverse. So that is what we have over here. So if you combine this, and this equation, maybe if you recall this as equation 1, if you're recalling this as equation 2, and if you call this as equation 3, you will be able to figure out what should be the control input tau so that the system will follow this behavior. Right? That is how you, for example, like if you want, if you still are not convinced, I can show you. So comparing 1 and 2, if you can say j dot of zeta from 1 and 2, j dot of zeta plus j zeta dot, this will be eta desired double dot plus k1 eta tilde dot plus k2 eta tilde. So I'll call this as equation 4. Then maybe I'll write it here. So now comparing equation 4. So substituting 3 in equation 4, what will happen? So instead of this zeta dot over here, you can substitute this here, right? So that will become j dot of zeta plus j of zeta dot would be nothing but d inverse tau minus n of zeta, right? Then what are the remaining terms? This would be equal to eta desired double dot plus k1 eta tilde dot plus K2 eta tilde. So from here, can you find the control input? From here, what is the control input? So nothing but eta desired double dot plus K1 eta tilde dot plus K2 eta tilde. Then you will have to subtract this term minus J dot of theta. Then what else you have to do? You will have to re-multiply this entire term with respect to minus J inverse. Then again, you have to multiply it with D. Then you have to add it with N of theta. This is nothing but torque, actuation vector torque. So if you supply this control input tau into the robotic system, then you can guarantee that it will follow this second order aerodynamics. Okay. Second. Yeah, sorry about that. Where are we? Yeah, second order aerodynamics. Yes. So that is how we get this equation for whatever we have got. Okay, so that's about it. So this is about closed loop dynamic controllers. So we can also see what are the feedback terms or feed forward terms. So this is a pure feed forward term because this and probably this, because these are coming from the trajectory planner, and these are feed forward terms. And what are the feedback terms? These two are the feedback terms because it consists of eta tilde dot and eta tilde, where eta tilde dot is nothing but the difference between the desired and actual position coordinates. And the actual position coordinate is what you obtain from the sensor. So it will be fed back into the controller so that you can estimate this parameter eta tilde. So that makes this a closed loop dynamic controller. This is also called a computer torque controller, right? Yeah, so that's about it. I will stop with the summary for week 7. We'll discuss probably a few questions regarding week 6. Unless if there are any more questions or doubts. Okay, so what does question 1 says? So question 1 says the seamless integration of inaccuracies, inaccurate models and limited sensing capabilities are known as. So we are being given with different paradigms, actually: classical robot paradigm, probabilistic paradigms, modern robots, hybrid robots. We have covered this in the previous slide. If you want, I can recall all these paradigms or the evolution of the how the motion controllers are deployed. So the statement says the seamless integration of inaccurate models and limited sensing. So that is what pretty much we are more or less dealing with these days. So if you look at this probabilistic robots, so that considers or that accepts that the model is basically inaccurate, right? That's what inaccurate models, because we cannot 100% estimate the parameters of the model. And the data from the sensors are also limited because sensors could also have some sort of errors. It could also have, inherent noise and all those things. So fusion between inaccurate models and limited sensing is what probabilistic robots is all about. So in that regard, the correct answer is indeed probabilistic robots out of all the 5 paradigms that we have discussed. So that is indeed the correct answer. Okay, now moving on to question 2. What does it say? The inverse differential kinematics or inverse dynamics is equal to a feedback or a closed loop, a feed forward and open loop, a motion-based control, a robust control, an adaptive control, and optimal control. So which of them is actually true? Is it a feed forward or is it a feedback? So you know what this, for example, I'll only consider this inverse differential kinematics that is applicable to inverse dynamics also. So you know the differential kinematics law, that is nothing but eta dot is nothing but J of psi multiplied by zeta. This is forward differential kinematics. So in the sense, like if you know this actual the control input zeta, you should be able to know what this velocity is in inertial frame of reference with using this law, using this transformation. Then what about this? Zeta would be j of psi inverse eta dot. This is nothing but inverse differential kinematics. So if you have a desired trajectory to track, how should the control input look like, or how should this vector be? How should it be? So for example, if you have a desired over here, if you have a desired vector of positions with respect to the initial frame of reference to be tracked, then using this transformation, you will be able to estimate the control input. So this is exactly what this inverse differential kinematics basically demands. And based on this, can you see or can anyone say whether this is an open loop or closed loop control? So what are the feedback terms? In order for you to find whether it is an open loop or closed loop term, you only need to hunt for or check for feedback terms. What are the feedback terms? Are there any feedback terms here at all? Is there anything that is coming from the sensors? Anything coming from the externality sensors? No, because in this control law, there is no parameter that is actually coming from the sensors. Jacobian is basically an inherent property that is associated with any mobile robot. And eta desired dot is nothing but the velocities of the desired trajectory that is coming from the trajectory planner that is being supplied by the user themselves, which is not coming from the sensors. So in that regard, there are no feedback terms. We'll say there aren't any. So that makes this a totally feed forward or an open loop control. Right. So in that regard, this is nothing but an open loop control, the only valid option. So we'll check this answer. That is indeed the correct answer. Okay, now moving on to question 3. Yeah, it says the robust control aims at controlling with a small error a class of robot manipulators. Model is not accurately known with the same controller. So like we have earlier seen the exact definition of a robust controller. So if you know that the parameters of the robot lies within a bound, maybe a lower and an upper bound, the robot can still be controlled using the same controller. It does not have to take any more information into account. So it's in that regard, it's also called an overwhelming control because the input that we would be giving is much more adequate than what it is actually being required. It will also accommodate for the change in parameters. So that makes it essentially a robust controller because even if there is an external disturbance or if there is a change in parameters due to some wear and tear or maybe some external differences, the robot can still be controlled using the same controller. So that makes that controller robust, right? So that indeed makes it robust. So the answer is indeed true, right? If you want to check the definition of robust controller, it says aiming at controlling with a small error a class of robotic manipulators. The model is not accurately known with the same controller. So that exactly is what is being asked on the question. So the answer is indeed robust control. Yeah, so the answer is indeed true. And moving on for question 4, what does asymptotically or exponentially stable means? So So like we have covered this during the design of uh, closed loop velocity and dynamic control, kinematic and dynamic control. So like initially, if you have an error, like I'll plot this axis as this error axis, and if I plot this as the time axis. So if initially, if you have an error, and as the time progresses, you see that the error is actually asymptotically tending to zero. This is what we call it as asymptotically stable, right? It should tend to zero. And what are these options saying? Like for example, the differential equation eta tilde dot plus lambda times eta tilde equal to zero. So this differential equation, in this case of this differential equation, the dependent variable eta tilde would basically tend to zero as time tend to infinity. So what are each of these options saying? So when time tends to infinity, the tracking errors tends to infinity. So that is obviously false. So it says the asymptotic stability means as time tends to infinity, the errors should also tend to infinity. It will be something like this. So like you cannot call something to be stable if the error is actually tending to infinity, right? So that inherently makes this option false. Option B says when the time tend to infinity, the tracking errors tend to be bounded. For example, if you have bounds, maybe this is an upper bound and this is a lower bound. So the second statement says as time tends to infinity, you can control the error within these two bounds. It could be oscillating or it could be constantly varying within this bounds, or it could be somewhat like this, oscillating and the the damping amplitude could decrease and eventually it will be like this. But still, that does not fit with the definition of asymptotic stability. The error is still not going to zero, so that makes it false as well. What about option C? When time tends to infinity, the tracking errors tend to be zero. So this is exactly the case that we are looking for. So that makes option C as the correct option. And all the other options does not is not even correct at all, right? When time tends to zero, so it says time tends to zero. This has nothing to do with stability. We should know what the behavior of the system as time tends to infinity, not at time tends to zero. So you don't even have to consider this at all. So the correct option is option C. Yes. Okay, now moving on to question 5. It says in a set point or a regulatory position control, the desired position vectors and velocity vectors are continuous. So is it true or false? So what are set point and regulatory control? So if you can recall from the lectures, see the set point control basically only deals with the initial position and the final position or the final configuration. It does not really consider how these two configurations have been realized. The only matter is initial configuration and final configuration. And the the information of the trajectory, the velocity and position in between these two configurations is irrelevant. And that is for set point or regulatory control. And in case of a trajectory tracking or a server control, we have an initial configuration. We also have final configuration. And each individual time steps, each individual configuration is relevant actually. We want the robot to track exactly as per the desired trajectory. So that is about trajectory tracking. So in order for us to realize this desired trajectory, the trajectory has to be continuous. So we should be aware of, or we should be provided with the position, velocity, and acceleration information. And that is not the case for regulatory control. You can consider you only need this initial and final position. The velocities and accelerations can be considered to be zero. And what does the question says? It says, in case of a set point control, the desired position and velocity are continuous. That is actually false because It need to be continuous only for tracking, trajectory tracking or servo control. It need not be continuous for set point control. So that is indeed false, which is our correct answer. Okay, so moving on to question 6. The second order aerodynamics is stable as per the following condition. Which of this condition is actually correct? So, if you can recall, I'll write the second order dynamics equation, eta tilde double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde should be 0, right? And this means if you compute the complementary function of or the homogeneous solution for this equation, you can see that eta tilde will tend to 0 as time tend to infinity, and same is also true for eta tilde dot. It will also tend to 0 as time tend to infinity. And in order for this to happen, the coefficients lambda 1 and lambda 2 should be greater than 0. So this will only be possible if and only if lambda 1 comma lambda 2 are both greater than 0. Right? The homogeneous solution would be maybe lambda tilde would be something like C1 e raised to minus lambda 1 t plus C2 e raised to minus lambda 2 t. This is how it look like. No, it's not really lambda 1 or lambda 2. It's maybe minus S1 t and minus S2 t. And this will be only minus S1 and minus S2 if and only if lambda 1 and lambda 2 is 0. And as you can see, as time tends to infinity, this term will go to 0 and this term will also go to 0. That makes the system asymptotically stable. So in order for us to realize this stability, as time tends to infinity, we want the error to be 0 so that both of these terms should go to 0. It is necessary that lambda 1 and lambda 2 both are greater than 0. So in that regard, which of the option is correct? I believe this is the correct option. Right? We can check the answers. Yes, so that is indeed the correct answer. Okay, now moving on to question 7. The velocity, the vector of input commands or control inputs of a computed velocity control is given as, in the case of lambda greater than 0. So which of this option is correct for computed velocity command? So what is this computed velocity control? So we know, as per the kinematics, we know eta dot is j of psi multiplied by theta. I'll call this as equation 1. And since this is a first order system, so we are neglecting dynamics at this point. We want the error dynamics to follow this first order differential equation, eta tilde dot plus lambda eta tilde. This should be 0. We want the system to follow, the error of the system to follow this first order differential equation, because I'll label this as equation 2, because this will guarantee that as time tend to infinity, if this is eta axis, the error would asymptotically tend to 0. Right? So yeah, on further expanding this, what is this eta tilde dot? Eta tilde dot is eta desired dot minus eta dot plus lambda eta tilde. This should be 0. So if I bring this to this other side, you will get eta dot would be eta desired dot plus lambda eta tilde. So I'll label this as equation 3. And from equation 1, what is eta dot? And from what is equation 3, what is eta dot? So if I compare 1 and 3, compare 1 and 3, you will get j of psi Theta would be eta desired dot plus lambda eta tilde. So if I bring this Jacobian to this other side, theta would be j of psi inverse eta desired dot plus lambda eta tilde, where theta would be our control input. So this is essentially the computed velocity control, right? Like in order for the system to follow this first order aerodynamics, the control input theta should be this, which makes the correct answer to be, I believe, option D. I suppose for question 7, that is option D. Yes, that is indeed option D. Now moving on to question 8. What is the primary or important control objective? So what are the primary objectives actually? Like I think, yeah, we have actually seen in the previous slide, we have seen the various control objectives. So out of which we have also established the primary control objective, right? So like even though we want the robot to, if we design a controller for regularization or trajectory tracking, the first and foremost important control objective is still the stability. We have to ensure that the system is stable, because whatever we have concerned in this course would be d of theta dot plus n of theta is inherently unstable, because if you give a constant control input force, a control actuator input, and as there are no dissipative terms here, you can see that the system will eventually speed up or it will eventually accelerate. So that makes it inherently unstable. So in order for us to do that, the first and foremost important thing that we have to ensure is to maintain the stability. So that should be the prime most important criteria while designing a robot controller. So yeah, in this regard, the correct answer is indeed stability of the controller. And question 9 basically says something dash is the change of state at any instant in time or body or bodies. It only says the change of state. It can be position, it can be torque or anything. Something has to do with the change of state at any instant in time of a body. That is one of these three options. And the second statement is dash is the state of a body or bodies over a period of time, right? And dash is the position of a body or bodies over a period of time without worrying about velocity or higher order terms. And the given options are motion, trajectory, and path. So like we'll go with the easiest statement. I think the easiest should be statement 2. Dash is the position of body or bodies over a period of time. Sorry, I think that is the third. We'll go with the second. Dash is the state of the body or bodies over a period of time. So that basically means we should be knowing the state of the body, be whether it is position, maybe at a time t, we should be aware of its position, its velocity, and its acceleration. So this entire specification of position, velocity, and acceleration would give you the specification of the body at a particular instant of time. So that makes this definition to be of the trajectory, because in trajectory we cannot neglect the dependence of position, velocity, and acceleration. So that makes it trajectory. And dash is the position of the body or bodies over a period of time without worrying about velocity or higher order terms. So we still need to predict, or we still are concerned about the position of the body over a period of time But still, we are not really worried about at what instant or at what point of time does a robot reach this specific instant. Like it can actually try this trajectory however it wants. It is not bounded by time constraints. So that is a clear-cut definition of path, right? Still concerned about the position of a body over a period of time, but it's not really worried about at what instant each of these points of this path are realized. And the first only that leaves us with motion actually for the first fill in the blank. That is nothing but the change of state at any instant of time. So whatever a body, if the body is in an initial configuration like this, I'll call this as X and Y. And at any other instant, it changes to a different configuration, maybe X and Y. This is basically denoting the motion of a body. It's only denoting the change of state, right? That's about it. So I think the correct answer is motion trajectory path, which is option A. Okay, now moving on to question 10. Which of the following are open loop control laws for land-based bio robot? Is it inverse differential kinematics? Because you know the dynamic model of the robot, that is nothing but tau is nothing but d of theta, theta dot plus n of theta. So what is inverse dynamics? So if you specify the trajectory of the robot in terms of theta, theta dot, or rather eta, eta dot, and eta double dot, you should be able to find the actuator inputs. So that is what inverse differential kinematics is about. And are there any feedback terms in inverse differential kinematics? There are no feedback terms. There is no feedback terms that is coming from the sensor. So that makes this open loop. Inverse dynamics is open loop. And what about computer velocity control? So I'll straight away write this control law because we have derived this one or two times during this lecture or during this session. That is theta is nothing but j of psi inverse eta desired dot plus lambda eta tilde. So obviously there is a feedback term here. This eta tilde is a feedback term because eta tilde is eta desired minus eta actual. And this eta actual is coming from the sensors as a feedback. So that makes option 2 a closed loop law. So what about this PID control? PID is a model-free control. It does not have anything to do with model. So you can simply define a PID control law as tau is Kp. Well, how would that be? Kp multiplied by eta tilde plus Kd eta tilde dot plus Ki into integral of eta tilde. You can define this to be the PID controller, where this is the P term, this is the D term, and this is the I term. And if you take a look at this, each of these terms have this eta tilde, that is nothing but eta desired minus eta actual, and eta actual is from the sensors. So again, that makes PID control law as a closed loop, but model-free control law. Okay, so I think I have made a small mistake. This is inverse differential kinematics. So option 4 is inverse dynamics control. So that is whatever option we have covered in the first is inverse dynamics control, right? And inverse differential kinematics is also similar to inverse dynamics. So that is also an open loop law because theta is nothing but j of psi inverse eta desired dot. So again, since there are no feedback term, this is also an open loop control. So you can also call this as open loop. And computer control law, similar to computed velocity control, this is a closed loop, and cascaded is also closed loop. So the question basically asks the open loop control laws, which are inverse differential kinematics and inverse dynamics control law. So in that regard, we have two correct answers, that is option A and option D. Right? I hope there are no more questions on that. Okay, now question 11 is identify the incorrect statements. So the first statement is model-free control relies on pure sensing based on feedback only. Model-free means without considering the kinematic or dynamic model, totally relies on pure sensing. So that makes sense. This is a true statement. What about statement 2? Model-based control laws are easy to use, but are sluggish and produce poor tracking performance. That is something that is we have earlier seen that it is only true for model-free control. It is not applicable for model-based because since we already have the model, execution is very efficient. It won't be sluggish. So that is false. Third statement says model-based control are comparatively efficient and simple. That is true. Fourth says model-based control, accurate models of the system should be available. That is also true. So the incorrect statement is basically option 2, because that is what the question basically asks. And this is the incorrect statement. Okay, so we'll check the answer. Yeah, as you have seen, if I can, I'll reproduce a screenshot from the lectures. Model-free control, the defining features of model-free controls are they rely on pure sensor-based feedback and they are easy to use but are sluggish. But in case of model-based control, they are efficient and simple, but accurate model should be available. So in that regard, whatever we have said, option B is indeed the correct answer. Okay, so moving on to question 12. The necessary condition for the feed-forward velocity control to work without failure is which of the options is correct? So this is the feed-forward velocity control law. I'll just highlight it. Feed-forward velocity control law. In order for this to work, eta desired dot, this should not be equal to 0. Because if this is 0, this entire term would be 0. So there won't be any control input. So that is one requirement. And what is the other requirement? That is nothing but initial position of desired trajectory should be equal to initial position of actual trajectory. Then only this will work, because if you have this to be desired initial and this is desired final. For example, if your robot is also starting from the desired initial, it will basically track to the desired final. As per this control law, it will track something like this. But if your actual initial is somewhere else, and if you are still using this control law, feed forward velocity control law to work, this will be the actual final. And as you can see, there is always going to be an offset between the desired and the actual position. So this will not work. So apart from this condition, the initial position condition will also have to be ensured. So in other words, eta desired at t equal to 0 should be equal to eta actual or eta at time t equal to 0. So this is condition 1 and this is condition 2. So both of these conditions will have to be satisfied in order for the feed forward control law to work. So I believe the correct option in that case is option A, question for question 12. Yes. Okay, that is indeed the correct answer. Okay, now moving on. This basically says the controller of a land-based holonomic mobile robot is required to have the following aerodynamics. So we want the robot to track as per this aerodynamics law, so that as time tend to infinity, this error will asymptotically tend to 0. And this eta tilde is defined to be eta desired minus eta. So this is not an equal sign, this is eta desired minus eta. So if the governing equation of the robot in kinematic level is given as so and so, eta dot is j of eta multiplied by zeta, what should be the control input in zeta? So we have already covered this. This is nothing but the computed velocity control law. Right? So if you simply expand this, it will be eta desired dot minus eta dot plus lambda eta tilde. This will be equal to 0. And if you rearrange this, it will be eta dot would be eta desired dot plus lambda eta tilde. And from here, if I substitute this into this, you will get j of eta multiplied by zeta would be eta desired dot plus lambda eta tilde. So that makes the control input zeta to be j of eta inverse eta desired dot plus lambda eta tilde. Right? So if you give this as the control input, your robot will behave as per this aerodynamics law. So in that regard, the correct answer is, I suppose, option C for question 12. Yes. Oh, sorry, I think I forgot. Yeah, I've written this correctly over here. That is J inverse. But in the option, I've selected the wrong. I think the correct option is uh, this one. Yeah. An easy mistake to make. I actually didn't pay attention to this inverse, but here it is correctly written. So option E is indeed the correct answer. Okay, moving on to question 14. In case of holonomic mobile robots, all three states, XD, YD, and SID cannot be simultaneously controlled. Is this true or false? So if you can recall from the live lectures, we have seen how we control non-holonomic mobile robots. For example, in the case of a differential drive robot, for example, if this is a differential drive robot, if I label this as XB axis, this is YB axis, and this is the initial position, and we want the final position of the robot to be something like this. So this is XB, this will be YB, and these are the tools. So in case of a mobile, in case of a holonomic, non-holonomic robot, this is a non-holonomic. Because as you know, in case of a differential drive robot, you have this U, V, and R components to be maybe U, maybe some finite quantity. V will always be 0. and R will also be some finite quantity. The reason R being 0 is because in case of a differential drive robot, which is an example of a non-holonomic robot, the conventional wheels will provide infinite resistance along the lateral direction. Infinite resistance along lateral direction. So that is what is contributing to this V to be 0. So in case of this non-holonomic robot, in order for it to reach this final configuration, it will have to first do this problem as a line of sight. It can actually orient uh, this x-axis along this line first, and it needs to reach this position first. Then once it has reached this position, then it can orient it. So first it will be a position problem, then it will, orient. It's basically, if you want, you can call it to be a two-stage problem. But in case of a holonomic robot, the position and orientation are achieved simultaneously, because it can move along lateral and longitudinal direction at any orientation. So that is not a constraint for a holonomic robot. So what does the question says? In case of a holonomic mobile base, all the three states XD, YD, and XID cannot be simultaneously controlled. So that is actually false, because you know for a fact that holonomic robots, for example, this mechanical wheel robots and omni wheel robots, and even the servo drive robots that we have seen in week 2, they can realize all three coordinates XD, YD, and XID independently and simultaneously. So that makes this statement false, right? Okay, now moving on to question 15, it says the controller of a land-based holonomic robot is required to follow the second order aerodynamics eta tilde double dot plus k1 eta tilde plus k2 eta tilde, where eta tilde is eta desired minus eta. If the kinematic and dynamic equations are given as so and so, eta dot is j of psi multiplied by zeta, and tau is d of zeta, zeta dot plus n of zeta, then what should be the correct control input or appropriate control input so that the system will follow the second order aerodynamics? The reason it follows second order aerodynamics is that as time tend to infinity, the position errors eta tilde will tend to 0, and the velocity errors will also tend to 0. So that is why we want the robot to behave as per the second order aerodynamics. So if you expand, I'll label this as equation 1, equation 2, and equation 3. So if I expand equation 1, you can get it as eta decide double dot minus eta double dot plus k1 eta tilde dot plus k2 eta tilde. This will be 0. So if I take eta double dot to other side, it will be eta double dot would be eta decide double dot plus k1 eta tilde dot plus k2 eta tilde. This will be 0. So I'll call this as equation 4. Right? And from equation 2, if I differentiate equation 2, what will you get? You'll get eta tilde double dot would be j dot of psi zeta plus j of psi zeta dot, and from here zeta dot would be eta double dot minus j dot of psi zeta, the whole inverse, the whole pre-multiplied by j of zeta inverse. Or for example, we'll keep this as such. We'll keep this as equation 5. Would that be fine? Yeah. Now, if I substitute, mm, yeah, or okay, like for example, we'll take it further. So what will be zeta dot? Zeta dot will be uh, eta desired minus j dot of psi theta, the whole pre multiplied by j of psi inverse. This is zeta dot. I'll call this as equation 6. And if I substitute equation 6, right, if I substitute this theta dot onto equation 3, what will happen? So 6 in 3 would result in tau is d of theta, zeta dot is j of theta inverse, and instead of this eta double dot, I'll substitute equation 4, this term. Instead of this, I'll substitute this, right? So that will become eta desired double dot plus k1 eta tilde dot plus k2 eta tilde, right? So that accounted for d of theta, zeta dot. Yes, then we also have this term actually, minus j dot of psi theta. Then the remaining term would be this one, n of theta plus n of, sorry, plus n of theta, right? So if you plug this equation, if you give this as the control input, d of theta, j of psi inverse, eta is a double dot plus k1 eta tilde dot plus k2 tilde eta minus j dot of zeta plus n of theta. And you can also even reduce this theta as j of theta inverse eta, because everything should be brought back to eta, because eta is how you define the desired trajectory. But still here, as you can see, everything is still kept as such in theta, so you don't have to expand it any further. So if you give this as the control input onto the robot, you can make sure that the robot will follow this second order aerodynamics, and hence as a result, the position errors will converge to 0 and the velocity errors will also asymptotically reach 0. So this is about it. This is also this computed or control law, what we have. And I think the correct answer that matches this option is, I think option A, I think, right? Option A. Yes. So that's about it. Okay, so question 6. Now, what are the objectives of control systems? We have seen the primary objective being stability, but now it's asking all the objectives. Stability is one of them. Optimization is one of them. Regulation and tracking are also one of them, the control objectives. So A, C, and F in that case are the correct answers. If you want, you can actually recall this: stability, regulation, trajectory tracking, and optimization. So the correct answer are indeed A, C, and F. And moving on to the final question for this session, it's only a true or false question. A robust controller deals with uncertainties in a given system parameters, unknown constant parameters, and it requires precise knowledge of the structure of the system. So if you want to still, okay, we have already seen this earlier a couple of times. This statement is only true for adaptive controller, not for robust controller. Because in adaptive controller, it treats the constant parameters as unknowns, And because the system could be highly dynamic and we may not be able to estimate the constant parameters accurately at every instant. So in adaptive control schemes, we treat the constant parameters to be unknowns. Whereas in robust parameters, uh, it's the other case actually. We know the constant parameters and we know the bounds, the upper and lower bounds. And well, if the constant parameters are within these bounds, we can control the robot using the same controller without much of an issue. So since this is true for adaptive and not for robust controller, the statement is false. So yes, the statement only applies to adaptive control, not for robust control. Okay, so yeah, I guess we have one more question. Question 18. Yeah, finding the time history of position, velocity, and acceleration for a set of input forces, input torques is called something that links torques to position, velocity, and acceleration. D of theta, theta dot plus n of theta. So this is given. The input torques and joint forces are given. Our objectives is to find position, velocity, and acceleration. So if torque is given and if you are asked to find out the trajectory parameters, this is a problem of dynamics, obviously, but is it forward or inverse? It should be forward dynamics. And the other way is inverse dynamics. Yeah, so that is about, we have reached this end of the session. I don't have any further questions to discuss. Yeah, and since there are no more any questions, no more further questions, I'll wrap up this session. I hope you will go through this recorded lecture during your free time because the recordings will be available in YouTube. It will be shared. The links will also be shared to you. Okay, so until next week, see you then. Bye. Thank you.